All right, so let's talk about probability distributions. One of our biggest issues in probability is the difference between geometric and binomial models, and how to calculate those probabilities, those expected values. So our two different models are geometric models and the binomial model. The geometric model is when you have one success on the last trial. So what's the probability that my first basket I make is the 5th try? What's the probability of the first one I miss? In this case, I miss would be your successes, is my 10th try. The binomial model is we have a fixed number of trials. I'm going to take 10 shots. What's the probability I make 3 of them? What's the probability I make 4 out of the 5? What's the probability I miss 6 out of the 5? Or I'm sorry, 6 out of the 10. So that's your binomial model. It's more than one success in a fixed number of trials. It can also be one success, but you know how many trials, and it can be any of the trials. It doesn't have to be the last attempt. So both of these models are Bernoulli trials. Bernoulli trials have 3 things that have to be true. There has to be only 2 outcomes, success or failure. So you can talk about rolling a die. There's 6 outcomes on a die, but if you're only interested in an even, then an even would be a success and an odd would be a failure. If you're only interested in rolling a 6, then a 6 would be a success, and then the rest of the numbers would be failures. So they have to have only 2 outcomes defined. The probability cannot change, so your probability of success needs to stay the same. We've done a few problems where you're talking about a driver's test, and your first attempt, the probability of passing is a 36%, and after your second attempt, the probability of passing is a 70%. Well, that's not a fixed probability, so that wouldn't qualify as a Bernoulli trial. And then the trials must be independent. So the probability can't change. You can't use these distributions if you're pulling from a deck of cards and you're not putting the cards back. So there has to be replacement if it's that kind of trial. So we have 2 equations to use here. The probabilities for the geometric model, if you have nth trial or the x trial, you have x minus 1 failures, so it's q, the probability of failure to the x minus 1 power, times the probability of success, because you only have one of those successes. The binomial model has this nx, that's the NCR button, but generally we don't do that by hand, because it can happen anywhere in, say, 5 trials. There's lots of different combinations of the way you can get 2 out of 5 successes. So that accounts for how many different ways you can combine those successes. And so you have x successes, so it's p to the x times q to the n minus x. These 2 numbers need to add to n. Now, when it asks how many would you expect for the binomial model, that's your mean, n times p. For your geometric model, it's 1 divided by p. And your standard deviation for geometric is the square root of q over p squared. And for binomial, it's the square root of npq. And that sets up our probabilities for the sampling distributions. All right, so let's look at a few examples here. These examples are out of the book. I tried to find some released free response questions, and there were not very many that actually dealt with these exactly, so my guess is they're mostly going to be multiple choice problems. But an Olympic archer is able to hit the bullseye 80% of the time, so our P is 0.8. Assume each shot is independent of the others. If she shoots 6 arrows, what's the probability that each of the following results? Her first bullseye comes on the 3rd arrow. So we have the first is on this trial. So that is your geometric situation. So A is your 0.2 to the 2nd power. She has 2 failures. And then she has her first success on the 3rd times 0.8. And that is 0.032. Now, the other way to do this is to use the calculator command. Since I'm looking at one specific value, this is the Geomet PDF. I put in my probability of success, 0.8, and my success trial. The trial I have my first success, which would be 3. I also get the 0.32. This is in your second VARS menu as well, or the distribution menu. Okay, so B, she misses the bullseye at least once. So it tells us here she has 6 attempts. So B N is 6, and if she misses at least one time, remember that to do at least one, that means the probability that she misses 1 plus the probability that she misses 2 plus all the way up to the fact that she misses 6. So that's a lot of work to put into your binomial model. And so the easier way to do that is because probabilities must add to 1, the only option that's not included in at least 1 is that probability that she doesn't miss any. So the probability of 0 is equal to plus all of those probabilities equals 1. So we can say 1 minus the probability of 0 is equal to the probability of at least 1. So what's the probability that she misses? None. That's 1 minus 0.8 to the 6th power. If I was doing this into the calculator, I can do 1, so I got 0.738. The calculator command would be 1 minus binom PDF, 6 trials. We're talking about missing, so the probability is 0.2 and comma 0, and that gives us the same answer. Again, Geomet PDF and CDF, binom PDF and CDF are in your second VARS menu. PDF is a point density function, so PDF is one number, and your CDF adds up from 0 to the number you give it. So if I want above that, I have to subtract from 1. All right, let's look at part C. Part C, her first bullseye comes on the 4th or 5th arrow. So we are looking once again at geometric. Her first bullseye comes on the 4th or 5th arrow would be the geometric probability of 4 plus the probability of 5. So I have to do the point, let's see, her first bullseye comes, so 0.2 to the 3 times 0.8 plus 0.2 to the 4 times 0.8. And when I plug that into the calculator, I get 0.00768. And that's C. So part D, she gets exactly 4 bullseye. Now you're again looking out of those 6 arrows that she gets exactly 3. So D is binomial, 0.2 comma 6. This is how you would describe the model. We can say she gets exactly 4. That's probability of 4 out of 6. So if I'm going to do this by hand, it's 6 choose 4. And then 0.8 to the 4th and 0.2 to the 2nd. So our exponents add to the 6 trials. In the calculator, much easier to do. Binom PDF, because I just want exactly 4 bullseyes. And I put in 6, my probability of success. We're talking about making them, so it's 0.8. Oops, I closed my parentheses too early. And comma 4. And that is 0.246. E, she gets at least 4. So at least 4 again means a probability of 4 plus the probability of 5 plus the probability of 6. So I can plug those into this. So I can plug all 3 of these into my binomial equation and add them up, but that ends up being a lot of work. So what we did was we said the probability of at least 4 is equal to 1 minus the probability of 3 or less. And so to do that in the calculator, I do 1 minus binom CDF 6, 0.8, 3. Notice this number is decreased by 1 because if I include 4, it's going to add up 0, 1, 2, 3, and 4. What I want is 0, 1, 2, and 3, so then when I subtract it, I'm left with 4, 5, and 6. So when I plug this into my calculator, note again, it's CDF because I want it to add up 0, 1, 2, and 3. I get 0.901 for that probability. And then F is she gets at most 4. So F, at most, that wording is the probability that she gets less than or equal to 4, which is just binom CDF 6, 0.8, 4. I'll pull that back up. And I got 0.345. So hopefully, just looking at these examples one more time kind of refreshes your memory about the difference between the two models. Let's look at some more examples when they ask, how many bullseye do you expect her to get out of 6? Now we're talking about an expected value, a mean. So our expected is the mean, so our mean is n times p. So for A in this case, it is 6 trials with a probability of 0.8, which is 4.8. So that's how many we expect her to get. We don't need to round it because it's an average. And then with what standard deviation? That's using our formula square root of NPQ. So B is 6 times 0.8 times 0.2, square root of all that. Plug that in. So when I plug that into the calculator, I get 0.9798 or 0.98. And then see if she keeps shooting arrows until she hits the bullseye, how long do you expect it to take? This is asking you for the geometric mean, which is 1 over p. So C is 1 over p, which is 1 over 0.8, which is 1.25. So we don't expect it to take very long for her to make a bullseye. It'd be longer if you were asking how long it would take for her to actually miss. Those are your means, expected values. And then here's some more. Suppose your archer is now shooting 10 arrows, so your n is changing. Find the mean and standard deviation of the number she gets. So A is 10 times 0.8. We expect 8 with a standard deviation of 10 times 0.8 times 0.2. Let's see. 1.26. So B, what's the probability that she never misses? Meaning she made all 10 arrows, so that's 0.8 to the 10th, which is 0.107. So never missing is probability of making all 10 shots, so 0.8 to the 10th. B, that's 1, it's not C, it's 2. there are no more than 8 bullseyes. So probability that x is less than or equal to 8, which is binom CDF, because I want to add up from 0 all the way to 8. 10, comma, 0.8, comma, 8, which is 0.624. And then part 3, there are exactly 8 bullseyes. That's binom PDF. And so we have, remember, 8 out of the 10. Remember, the geometric only is one success. So binom PDF is the same numbers, but it's not adding it up. So .301, or 302 if I round correctly. And what's the problem? She hits the bullseye more often than she misses. So that means she's making at least 6. What's the probability of at least 6 bullseyes? So that's 1 minus the probability of less than or equal to 5, which is 1 minus binom CDF 10, comma, 0.8, comma, 5. And that's 0.967. Okay.